We're going to cover the quotient, product, and chain rule today. We're going to start by reviewing some of the rules we already know. We do know the derivative of a constant function, if f of x is equal to a constant, then the derivative of f of x is simply 0. Again, remember a constant function is just a graph of a horizontal line, and your derivative gives you the slope, and we know the slope of a horizontal line is 0. We do have our power rule for integers, and it's actually for general power rule, so it's, even though this is power rule for integer, we know this holds for any exponent n, the derivative of x to the n, we bring the n down. This is n, x to the n minus 1. This is one of the basic rules we learned to begin with. We also learned the derivative of the natural exponential function. The derivative of e to the x is e to the x. This is a very powerful concept. In fact, this is the only function whose derivative is itself. This leads us to where we want to go today, which is our three rules. The first rule we're going to look at is the product rule. The product rule basically says we have two distinct functions, u and v, and I'm multiplying these functions together. Instead of multiplying these functions out and then taking the derivative, can we actually take the derivative straight from where we're at? What is the derivative of u times v? Well, the derivative of u times v is u times the derivative of v plus v times the derivative of u. In other words, you take one function, hold its constant, and multiply it by the derivative of the other, and then add that to the other function held constant times the derivative of the du dx. Let's see how this works. Here we have two separate examples. I'm going to look at two functions, w equals x times e to the x. I have two distinct functions, an x and an e to the x, and my product rules is the derivative of u times v is u, dv dx plus v du dx. Well, clearly my u is my x, that's a distinct function unto itself. My v is e to the x, so its derivative, this is going to be u, which is my x, times dv dx, and again, derivative of e to the x is just e to the x, plus e to the x times du dx, and the derivative of x is just 1. And when we get our final answer, I went ahead and factored the e to the x out, and we get e to the x times x plus 1 is our final answer. We have a section function r. r is x minus 9 times x squared plus x. Yes, we could go ahead and FOIL this out, multiply it, and then take its derivative. We want to practice our product rule. Our product rule says this is our u, our first piece, and this is our v, our second piece. So the derivative is going to be u times the derivative of v. So u is just x minus 9. We hold it constant. The derivative of v, the derivative of x squared plus x, is 2x plus 1. And then we add that to v. We bring v down, and the derivative of u, the derivative of x minus 9, is simply 1. And again, we can FOIL this out and then combine like terms, and we get our final answer. What we should note is if we would have sat there and FOILed this out to begin with and then took its derivative using our general power rule, we would have gotten the exact same answer. Here's a couple more examples. Here again we have a product rule. A 1 plus x squared times x to the 3/4. Our 1 plus x squared is our u. Our x to the 3/4 is our v. So this is going to be u times dv, which is 1 plus x squared times 3/4 to the x to the negative 1/4, plus x to the 3/4 times 2x. What I did is I factored out x to the negative 1/4, distributed it in the 3/4, and when I factor in x to the negative 1/4 out of the x to the 3/4, I just zoom in with an x. So we get 3/4 plus 11/4 x squared times x to the negative 1/4. Again, we could have sat there already and multiplied, distributed this in, and taken the derivative. We're trying to get a practice on the product rule. Just to let you know, this x to the 3/4 you're probably not going to see in your homework. I just want to give you an example of it. A little bit, I have the ability to identify the distinct functions. You're going to see something more like this r, which is 3 minus x squared times x cubed minus x plus 1. Again, my u is 3 minus x squared. My v is x cubed minus x plus 1. So this is u times dv. The derivative of v is 3x squared minus 1 plus v times du. Derivative of 3 minus x squared is negative 2x. Again, when we get to this step, we've taken the derivative. At this point, it's just our algebra. We need to distribute and combine like terms next. So we sit there and we multiply these polynomials and combine like terms, and our final answer is negative 5x to the fourth plus 12x squared minus 2x minus 3. I do not think your product rule is that difficult. The hard part is identifying when to use it, and then it's just a matter of doing it, and really you just need practice to master it. This is your quotient rule. And again, I'm going to have two distinct functions, u and v. They're both functions of x. The derivative of u over v is v du dx minus u dv dx all over v squared. I don't memorize it like this. I memorize it like this. The derivative of u over v is low d high minus high d low all over low low. This is the low function times the derivative of the high minus the high function times the derivative of the low all over the low squared. I find this much easier to work with, and this is what I'll be repeating throughout my lecture today. Here is a classic example of a quotient rule. Again, we obviously have a fraction. This is my high function, is my 4 minus 3x. My low function is my 3x squared plus x. And the derivative of this is low d high minus high d low all over low low. So there's my low times the derivative of the high is negative 3 minus the high times the derivative of the low is 6x plus 1. This is the kicker here. This is where I always trip students up. This is minus sign in between, okay? Because what happens is students forget to distribute it. They only put it to the first term sometimes, or they distribute it prematurely. What I mean by this is that you need to multiply these out. You need to FOIL these binomials here before multiplying by the negative sign. So when we go to simplify this, we distribute the first pair of polynomials, the negative 9x squared minus 3x. We leave the minus sign out front, then we FOIL the rest here. This is 24x plus 4 minus 18x squared minus 3x. We need to remember to distribute this minus sign into all of these before combining like terms. If you work this out on your own, you'll wind up with 9x squared minus 24x minus 4 all over 3x squared plus x. So make sure you work these out. Again, this is just going to take practice on your part. Here's another example. X squared minus 4 times x plus 0.5, again a quotient rule. So the derivative of the quotient rule is low d high minus high d low all over low squared. So low is x plus 0.5, d high, derivative of the high is 2x, minus high, which is just x squared minus 4, times derivative of the low, which is just 1. Again, it's just remembering to distribute that minus sign. This becomes 2x squared plus x minus x squared plus 4. This is all over my low squared, which gives us a final answer of x squared plus x plus 4 all over x plus 0.5 squared. Our last rule is going to be our hardest one, our chain rule. I want to give a brief introduction to it before we dive into it. A chain rule basically means you have a composite function. You have an f of g of x. G of x is your inside function, f is your outside function. This is what you're going to recognize as a chain rule. We're going to practice just putting together functions. If we have a function f of x, which is x over x plus 2, and g of x, which is the square root of x, let's compute the composite f of g of x. F of g of x, well, what we do when we do a composite function is we replace the g of x with its actual function. So this is f of the square root of x. We know f of x is x over x plus 2. Well, I'm looking for not f of x, but f of the square root of x, so I'm going to replace the square root of x everywhere I see an x. So the f of the square root of x is the square root of x over the square root of x plus 2. Now let's work backwards, pulling things apart. Say I have the function h of x, which is 3x squared plus 7, all to the 8th power. This is a composite function, and we can view this as h of x equals f of g of x, and we want to find f of x and g of x. We can view this as a composite function because we should notice there's two distinct functions here. There's an inside function, g of x, and there's an outside function, f of x. And if we view g of x as the inside function, we know it can be written as f of g of x, so g of x is naturally the inside function. And when we look at h of x, inside the innermost piece is this polynomial 3x squared plus 7. So we'll say g of x is simply 3x squared plus 7. Now, if f of x is the outside function, I already said g of x was this 3x squared plus 7, so what's left? Well, the only thing that's left is this 8th power. Well, it's something to the 8th power, so we're going to say f of x is x to the 8th power. So we've identified two distinct functions. G of x is 3x squared plus 7. F of x squared is x to the 8th. So what exactly does the chain rule say? The chain rule says when I have a composition of functions, when I have f of g of x, to take the derivative of f of g of x, I first take the derivative of f primed, leaving g of x alone. So I take the derivative of the outside function, and I don't touch the inside function, I leave it alone. And then I multiply it by the derivative of the inside function. The hardest thing here is really to identify your outside and your inside functions. And we'll practice this a couple times. An example, I have this polynomial. This looks like one of the examples we just did. I have 3x squared plus 5x minus 1 to the 4th power. As we said before, we can write this as a composition of functions. I have an inside function, this big polynomial, and an outside function, this 4. And your outside-inside rule says we take the derivative of the outside first, so we're going to take the derivative of this 4th power first, leaving the inside function alone. So when I take the derivative of the outside function, this 4th power, your derivative says bring the 4 out front, and then subtract 1. So I'm going to sit there and take the 4 out front, I'm going to subtract 1, and notice I leave the inside function alone. This is 4 times the quantity 3x squared plus 5x minus 1 cubed. I leave the inside alone. And then what I do is I multiply it by the derivative of the inside function. Well, the inside function was this polynomial. The derivative of 3x squared plus 5x minus 1 is simply 6x plus 5. Now, at this point in time, we're done with the derivative. We've actually calculated and we're finished. However, when we typically write our answer, we typically bring this 6x plus 5, this derivative of the inside, out front. So this is going to be our final answer. Y prime is 4 times the 6x plus 5, all times 3x squared plus 5x minus 1, quantity cubed. Another example of this, I have e to the 5x squared plus 1. I want to take the derivative of this. Well, the derivative of this, we have an inside function, which is the 5x squared plus 1. A lot of times you ask yourself, how to identify the inside of the outside function? What do you plug into first? That's going to be your inside function. We clearly plug into the 5x squared plus 1 first. Your outside function is simply this e to this power. So when I take the derivative of the outside, remember your outside-inside rule, the derivative of e to the u is just e to the u. So this is the derivative of my outside function. Derivative of e to the u is e to the u. And then I'm going to multiply it by the derivative of the inside function. The derivative of 5x squared plus 1 is simply 10x. So this is 10x times e to the 5x squared plus 1. What are some general rules we can follow? Well, we have a chain rule for our current derivative rules. When we have u to the n, we're assuming u is a function of x. Derivative of u to the n, we bring the n down, u to the n minus 1, and then we take the derivative of du dx. Again, u is just some function, a polynomial, whatever we want it to be, and we follow our general power rule. We leave the u alone, and then we multiply it by du dx. Again, this is the same rules that we had before. This was the f primed g of x. This was the derivative of the outside function, which is our power, and then we multiply by the derivative of the inside function, which is the u. This is basically what we're doing. This is the u to the n. This is u to the 7th. So this is 7u to the 6th. We bring the u down, leave it alone, and then we multiply it by du dx, and the derivative of the inside is 15x squared minus 4x cubed. And again, when we write our final answer, we basically bring this out front. So 7 times 15x squared minus 4x cubed times 5x cubed minus x to the 4th, all to the 6th power. We can expand this to our e to the u function. The derivative of e to the u is e to the u du dx. So we bring the e to the u down because the derivative of e to the u is e to the u, and then we multiply by the derivative of what's inside. For example, e to the negative 5x. The derivative of e to the negative 5x is simply e to the negative 5x times the derivative of stuff inside, and the derivative of stuff inside, the derivative of negative 5x is negative 5. And when we write our final answer, we bring the negative 5 out front. So negative 5 e to the negative 5x. You can go straight from the first step to the last step if you care to, if you're able to see it. This is just putting the du out front. And finally, e to the 2x over 3. Well, again, the derivative of e to the 2x over 3 is e to the 2x over 3 times the derivative of 2x over 3, which is just 2/3. So your final answer is 2/3 e to the 2x over 3. These rules are going to take a lot of practice. Please make sure that you work them multiple times. Don't just use all your help tools to get the answers. Make sure you can do them backwards and forwards, and we will take questions on these in class next time we meet.